Okay, let's start. So, welcome to the Heidelberg Joint Astronomy Colloquium of today, this week. And it's a great pleasure to have our guest and speaker, Barbara Ercolano from the Universität Sternwarte München, the Ludwig-Maximilians-Universität in München. Yeah, so she and I know each other already quite a long time. We have also been collaborating a lot. So Barbara started her work being a radiation transfer expert. So she actually is the designer and maintainer of the well-used Moccasin radiation transfer Monte Carlo code for computing radiation transfer in ionized media, and which is a public code, right? So everybody can use it. So you can anyone brave enough, yeah. Anyone brave enough can use the code. So she's at the moment she's professor of theoretical astrophysics at the university in Munich since 2010, and did her PhD in UCL in London, right? And that's where she did the work on the radiation transfer. And then she moved to Harvard, Smithsonian CFA in the United States, and then had a advanced fellowship at the Astronomy Institute of Astronomy in Cambridge, also working with Kathy Clark, right? Yeah. Right. And then moved to you went to the UCL in London first before you went to Exeter, right? Or
UCL at Cambridge at the same time, so I had a split fellowship.
That's okay. I wasn't aware of that. Okay, so then she moved briefly to Exeter, but then there was the call from Munich. And well, she couldn't resist the temptation, also because in Munich there are much higher mountains than in Exeter, and being a climber, right. So she used then the radiation transfer expert also to apply that to protoplanetary disks, and found that you can do really nice models of disk photoevaporation, so the destruction of protoplanetary disk by the star itself, and then actually also started working on planet formation and all other aspects of protoplanetary disks. So she actually also has held some important positions. For instance, she was the spokesperson of a Forschungsgruppe or research unit of the DFG, which is a kind of collaborative network here in Germany working on transitional disks. And she is the speaker of the Origins cluster, excellence cluster in Munich, so a very important position. I hope that she will still be able to do science in spite of all the responsibility. Yeah, we're looking very much forward to hearing about the science. So the stage is yours.
Okay, now I'm terrified after this introduction. So, but thank you. Thank you very much, Kes. And indeed, it's a pleasure to be here with lots of friendly faces. And Heidelberg has been really the center of this collaborative research unit network that we've had already now for 2 periods. It's coming to an end at the end of this year. This is why here I would like to show a lot of results that we had from this very nice collaboration with the group of Kes and also other people, as I will show you later. And also I will try to start telling you about our first steps into trying to understand really the connection, but the real connection about atmospheric gases, both in planets and in disks. So you might recognize this. This is a very badly made AI generated image of a protoplanetary disk with a young star and planet. So I made it myself. This is why it's so bad. But I only just put in young active star, protoplanetary disk with gas and dust and planet. And there it came out. And I think more or less says everything that I want to say today. So planet formation happens in the leftover material from the star formation process. This means that every star, so solar type star, has the potential, in fact, does make planets. But it also means that you cannot look at the planet formation process in isolation, but you have to put it in the context not only of this nursery, which is the protoplanetary disk, but also of the big bad star in the center, which is radiating in its environment. And this is what I'm going to talk about today. So why do you do that? Well, you do that first because you want to understand planet formation, but also because you want to explain observation. And we are now in the time of exoplanetary science, in which we have quite a large population of planets that are known. At the moment, we only know their mass on the y-axis and how far away they are from the stars. But we're getting more and more information also about the atmospheres. And this will become huge in the next couple of decades with the new missions coming in. But even if we just look at their mass and their orbital periods, you see that they span a really large area. And if you look at, in comparison, where our solar system planets are, Venus, Earth, Mars, you see they're not even in that region. That's not to say that we live in a weird system. This is just an observational bias. So you see the different color points tell you the different techniques that were used to detect those planets. So Kes actually gave me a pointer. Sorry, I don't need the stick. And so you see that these different techniques all have different biases. And of course, you know, our Earth and our planets are orbiting quite far away from the central star. And so you need to wait a long time until you have a few transits to confirm this type of planet. So our technological capabilities until now haven't allowed us to push the parameter space until our solar system. But this might happen now with Plato in the next years, not quite all the way down, but it will improve the situation. Still, a planetary solar system is not typical. This is because there isn't a typical planetary system. That is the point of this slide. You know, you have a diversity, and so if you have a planet formation model that can make the solar system, excellent. But it should be a planet formation model to make also other types of planets. And of course, if you look at it in the context of the protoplanetary disk and the star, you see that it's very easy to have this diversity. And so what's out there? There's a few very, very pedagogical slides. So I'm sorry for the experts here, but I was told to that you guys get credit for it. So you have to you have to see the slides as well. And so what's out there? Well, these are the typical exoplanet types that you see. So you have gas giants, so like a Jupiter. You have Earth, like a Earth, obviously, Neptune-like planets, like an ice giant. But there's also stuff in between that we don't even have in our solar system. So again, even if you're making the solar system, you're not making most of the planets that are out there. In fact, if you look at the statistics, and again, this could be biased by the observational techniques, but at the moment, we do see a lot of these super Earths. So it must not be that difficult to make this super Earth. And we don't have it in our solar system. How do you make planets? Well, as Kes, obviously, that's the first answer to that. And in fact, this slide is stolen from Till Burstill, lecture on planet formation, and Till obviously also comes from Heidelberg here in the group of Kes. And there are two main models, let's say. I would say that disk stability model hasn't been studied as much as the core-accretion model. So, of course, you know, we say, you know, the core-accretion model is the preferred theory at the moment. It could also be that, you know, we haven't really concentrated that much on disk stability. But let's start with the disk stability. So you can make planets the same way you make stars. So top down, which basically means you are in the disk and a clump of gas and dust in the disk collapses. under its own gravity and makes a object that is not heavy enough to basically burn for nuclear burn into atoms. So, which means it's not a star, it's a planet or a brown dwarf. But so this is what you can make through these visibilities. And let's say that, you know, there are reasons why this visibility theory has been a bit, let's say, not studied much at the moment, because there are problems in how you basically do allow the disk to collapse to make this kind of planets that we observe, the population of planets that we observe. But it might still be happening for some of the planets that we observe. And indeed, you can make gas giant that way. You can make ice giants if you strip away some of the gas, or if you collapse smaller clumps. There might even be placed giants made by this visibility that have then migrated close to the star, and they get photo-operated. And if in that time the heavy materials in the gas giants have collapsed in the center to form a core, you might strip away the fluffy stuff around and end up just with the core, so end up with a terrestrial planet that way. As I say, we won't talk about this visibility today. Actually, we won't even talk about core accretion today. But to put it into the context, the core accretion is this, that bottom up. So this is basically about going to the 13 orders of magnitude journey of small dust grains, micron-sized dust grains that are in the disk, having them basically come together, growing into larger blocks. And the way that you can do it is through different processes. You can invoke streaming instability, which is what people tend to prevent at the moment, to make larger clumps. And these larger clumps end up then in planetesimals, which then are fed all the pebbles in the disk and grow up into larger and larger cores. So you make them larger and larger until you end up with a terrestrial planet. And depending on where in the disk you have made this terrestrial planet, if there is still enough gas in the disk, you can accrete this very quickly, catastrophic accretion, and end up with a gas giant. So this is the way that you go. Or if you're far out in the disk, you can end up with an ice giant if it's cold enough. And so you see, depending on where this happens and how the conditions are in the disk, you end up with different planets. You also end up with different architectures. When we talk about architectures, we talk about where planets are in the system. And so there was the idea that our solar system is the way it is. So we have the terrestrial planet close in because it's less volatile, and then you have the gas giants outside because there's more. Okay, it could be, but actually out there we also see planet systems that are completely different. So that is very, very important to keep your mind open, that wherever you have made your planet, they can migrate and a lot of things can happen after that. And so let's put it into the context of disk. And I've shown this slide many times. So all that I've talked about until now is not just happening in isolation, as I say, it's happening into this protoplanetary disk. And the protoplanetary disk has the young active star in the center, as I mentioned in the beginning. And this star basically, stars, when they're young, they're much more active than older stars. So our sun, for example, was, when it was a young star, able to emit 10,000 times more X-rays than it does at the moment, because the magnetic activity on the young stars is much higher. So our sun looks like this at the moment. There's still some stuff going on. And imagine 10,000 times that stuff. It emits a lot of high energy radiation. Now, why do we care about these X-rays? Well, we care about the X-rays because they can penetrate large distances into the disk. You know, EUV radiation gets absorbed very easily by hydrogen, and so there's lots of hydrogen everywhere, so they don't penetrate very deeply. The X-rays, they, depending on their hardness, they have to wait until they have a cross-section that can absorb them. So generally, they penetrate deeply because they have to wait until a carbon, or they find a carbon of an oxygen, and their K shells sometimes, even if they're very high energy. And so there's a lot, obviously, much less carbon and much less oxygen in this gas. So the opacities are much lower for an X-ray photon than they are for a UV photon. So a photon at 13.6 eV has a very short life compared to one at 1 keV. And so they penetrate deeply, which means that they can bring action to the places where planets are trying to form. So they change the chemistry there very strongly. They bring ionization. Yoo-hoo, I'm back on track. So, and when you have an ionized gas, when you have a charged gas, then suddenly the gas notices that there's a magnetic field in the disk. If the gas is neutral, it doesn't care. But if the gas is ionized, it's charged, then it says, haha, here, I'm getting pulled around here. These magnetic processes become much more relevant. Recently, we have evidence of winds being driven by magnetic processes, which might be important for the evolution of the disk, or even dominate the evolution of the disk. Also, the X-rays just heat up the disk, and they heat it up to a point that some of the material in the disk can climb up the gravitational potential. At this point, the only gravitational potential that you have is basically dictated by the star, because the mass in the disk is about 1% of the mass in the star. And so the further out you are in the disk, the less this gravitational potential comes. And the small heating that these X-rays do, so to 1,000 Kelvin more or less, is enough for this material to become unbound. And then the disk is spinning. So the material is then basically accelerated outside that way. And so this is this complicated picture that the planet formation process is basically having to live with, which affects the way that the material is changing. And that lifetimes of all these things are basically the same. It's all a few million years. So everything is happening together. You can't decouple one thing from another. And so a few years ago, we tried to put it all together of what's happening where, and we argued to the point that then we decided not to make this this plot very sharp. So you see, we went drunk here. It was just that we didn't know where things stopped and where the others started. So this plot that Geoffroy Lesoeur and Mario Floch made is just basically to roughly give you an idea in a disk of a given extent in the x-axis, and this is the star is here and the disk is here. There's a lot of stuff that's happening. So the streaming instability, which is basically the first step to planet formation in the Milky Way. And then you have all these kind of like instabilities, MRI, magnetorotational instabilities. And then you have this photooperative wind, which you might say, well, this is only affecting the fluffy stuff at the top. Why does it even matter about planet formation? It turns out that it has a huge effect on the planet formation, because it can really affect the evolution of the surface density of the disk. So we tried to basically change slightly the photooperation profile, and this will become clear in a few slides, in a population synthesis code. So this is the way that people basically try to make population of planets by approximating all those complex physics into prescriptions. And they run it for lots of planets and see what comes out, and then they compare it with the surveys that we have at the moment. So this is basically population synthesis, planet population synthesis, and we changed nothing, only the photo operation prescription in this big, basically in this big recipe, and we ended up with completely different population. And so you see that that little fluff at the top is very, very important to actually understand what type of planets you make, both their mass, where you make them, and also obviously their chemistry. And so the photo operation model started well before we had all this information on planets. So why we even made photo operation models? Well, because people already realized a long time ago that disks around young stars were very short-lived in astrophysical senses. You can just look at the fraction of disks in basically in young stellar clusters and compare it amongst clusters of different ages. And you see that for the older clusters, the disks are gone. So the fraction goes strongly down. And so the idea is that disks only live a few million years. And you can argue about this point up here, whether this other process is going on. But if it's not a few million years, it's like maybe 10 million years. But, you know, disks are short-lived. You can also look at this in different infrared wavelengths. So 3 micron here, 20 micron, and look at the dispersal. So look at how this the infrared excess changes at these different wavelengths. And you see that basically the hot dust, the hot part of the disk, which is radiating at the lower, at 3 microns, for example, compared to 20 microns, goes away faster. And so this is another hint of how disks are dispersing. They're telling you that the stuff at the center is being removed faster than the stuff at the outside. And this is why we can say that disks are dispersing from the inside out. And these were the two boundary conditions for setting up dispersal models, of which photo operation was very, very successful in basically satisfying. So for the aficionados here, this is the classical disk, which has, this is the star, the photosphere, the star, and then the infrared excess is here. So this is all the dust basically outside in the circumstellar environment. And when you start removing the bit close to the star, then you get this dip here. And these are transition disks, the so-called transition disks, which now is a very, very mixed bag now that we have especially resolved observations, but every time we didn't, so everything was easy. So how does photo operation work? Again, in the good old days in which disks were only alpha disks, so they just had a viscosity that was allowing them to accrete mass onto the star. You have this view that basically mass is going in, angular momentum is going out. This may be slightly changed in the context of MHD winds, but you still have an accretion rate, so you still have mass going in. And for viscosity, so for MRI type of models or viscosity models, viscosity goes down, so mass accretion rate in the disk goes down as a function of time. This is because it's proportional to the surface density of the disk, which is going down as a function of time. However, you also have photo operation from the central star. So the star is irradiating the disk. Some parts of the disk get hot enough to climb up the gravitational potential. And you hit there at that point a mass loss term. Now you can see this mass loss term doesn't depend on the surface density of the disk. So it's constant through the life of the disk, more or less. It just depends on the luminosity of the star. And the mass accretion rate goes down. So at some point, photo operation wins, because this term is going down, it's trying to fill up the material, and this term is staying the same. When this happens, in the places where the disk is losing the most mass, you end up with a gap. Now, you hear a lot about gaps made by planets. They're different gaps. This gap here really is a gap. It's a clean gap. There's nothing there in there, and you cannot have material from the outside going in because you have a centrifugal barrier. So if you basically have material trying to fly off the outer disk, it just gets blown out outside. And so this type of gap really disconnects the inner disk to the outer disk. So the inner disk then basically drains away onto the star, and you have this basically left with this beautiful transition disk. So a disk with an inner clear cavity, which is now completely fried from the central star, and it's removed quickly from the inside out. And so this is clear. This is a picture that we now, everybody who's ever worked on this agrees on. And there's a lot of people who work on this, as you see. And you might think, well, why did so many people work on this? You know, it's okay. You want to know how this dispersed? Now, who cares? No, we want to know how this dispersed because we want to know how our planets form. And it turns out that each one of us has a different idea of exactly how much mass we are removing where. So this is an old plot, but it's the motivation, one of the motivation beyond the research unit that I will be talking about in a second. At the time, nobody agreed. So this is the mass loss, and this is the radius of the disk. And you see that different people just using, not because some people were stupid and some people were clever, we just used different approaches and different parameters, and we ended up with different answers. And so it's clear that, you know, okay, still we have the removal of the disk from the inside out in the correct lifetime of the disks, but we end up with completely different predictions for planet formation at all different levels of the planet formation process. For example, at the beginning, formation of planetesimals, streaming instability. Again, I'll skip a little bit. we had exactly at the same month, in the same 2 weeks, 2 papers came out doing exactly the same thing. Disk population synthesis, formation of planetesimal by streaming instability. And we came to completely different answers. And we did exactly the same thing. So look, they, the paper with Carrera and Gotti, they were producing a huge amount of planetesimal by the streaming instability thanks to photo operation. Look here, the size here, 10 to the 2 is here, and we have 10 to the 0 here. And look at where we create stuff. Everything is completely different. And the only thing that was changed was this little prescription, because the rest was exactly the same. And so we agreed to disagree. There's no way, you don't know who's right until you know how disks are dispersing. That was the point there. Also, if you just look at migration, so if you say, okay, we don't understand how planets form at the beginning, let's say planets have formed in the disk, and now let's push them around with the gas that is in the disk. Again, just change the photo operation curve. You end up with different architectures. So this is basically an histograms of how many gas giants you end up where. This is the distance from the star. And again, you just change this curve and you have a completely different histogram. So again, if you want to use this in population synthesis models, you better get it right, because there's no point doing anything else before you understand how much material is available for planet formation where, before you even start planet formation. You have to have the building blocks. And so that disks winds exist, we've known this for a very long time. So mid-90s were the first observations of emission lines spectrally resolved, which showed very slight blue shifts. There were no jets or no magnetic processes at the time, because these winds were very, very slow. They were just a few kilometers per second. So if you have a star with a jet, you see immediately there's hundreds of kilometers per second, even thousands sometimes. And so what we have here, this is 1 or 2 kilometers per second, maybe. And this can only be explained with a slow moving disk wind. So evidence for disk winds have existed already at the time in which we were setting up the research unit, but we didn't quite know whether our model could really be benchmarked by this. So, well, actually we were sure of it in 2010, in 2016. Look at how much we showed off in this paper, the smoking gun of X-ray photo operation. This question mark is not in the paper, but I put it on now because, as observers always do, they go and observe things at higher resolution. Just because they have a better instrument, they have to do it. And they ended up with this bloody thing here, which is like a second component to this line that shows that you don't just have a nice narrow component of photooperative wind, but you have something being emitted very strongly, very close to the star, where photooperation can operate. And so this was taken as the first evidence for also magnetic effects, magnetic disk winds close to the star. And in fact, if you have also beasts like this, and you can only fit them really if you have an MHD component. So we now know that the two things are happening at the same time. And we know that there might be some kind of evolutionary sequence that is being traced by these emission lines, in which you have at the beginning the MHD winds in the center and then the photooperative outside. And then you start removing the disk and you end up with only the photooperation out. So again, look at the date. This is 2017. This was the state of the art. This is where we decided to found our research unit on transition disks. And we started investigating all this, not just on a photooperative point of view or on a planet point of view, but we basically joined up forces and tried to attack this problem for all the possible different angles. And at the time, transition disks, so this disk with a gap, were really a backward, because we were just saying, okay, well, these are disks in transition. So if we want to know something about planet formation, we need to understand these objects. And so this is how we set up and how we convinced the DFG as well to allow us to do this project. And so we had different, different parts. We had the observational part. I was very much involved in this part with the evolution chemistry. Kaz was looking at the planet disk interactions. and then dust physics and planet formation. Of course, Kels and Till were also in there, and Paola, who was also here at the time, right? I think. So it was just a very, very fun project to work with. And I think it's been successful. You know, people were happy. We had a lot of papers. We had a lot of observations that we now want to try and put in a data set that is available for the community. And we have a lot of simulations, quite a lot of simulations. But again, also we have to try and somehow make it sustainable. And so I'll tell you something about what we found out on the B part, which was basically, I think we really now understand photo operation. We know there are differences between different models, but we also know what these differences are due to, which means that you can choose your photo operation model now according to the type of properties that you expect your population to have. And this is not something that we could do before. So we could quantify the mass loss rate. We could predict really the evolution of the planet making material by looking at how this then evolves with this prescription. And we study the outflows and their interaction with the planet formation. So I'll show you some quick results. So we basically, these are models of the disk winds. So this is, the star is here, this is your disk, and these are the streamlines of the wind. So these are different, showing you different things, the density, the temperature, and the velocity. And now with this stuff, imagine doing it down 400 or 500 times. So that you can parameterize it really for all the different type of stars, X-ray luminosities. We also looked at metallicities, and this is what you need if you want to then use this for population synthesis model. Because of course, you're not making one planet, you're making thousands of planets. And we have done it. Again, simulations still disagree when you look at different authors, but we now know why. So we now know, depending on what you want to do, why, for example, X-ray driven mass loss rate could be lower or could be higher, depending on the type of molecules you have in there, depending on the type of processes you think are dominating. So I think we really have improved. And we also, I think we have reached now, and this is not in the research unit, but it will come out soon, we have now developed a code that can solve the thermochemistry of the disk on the fly together with the hydro. So this is this Pluto Prismo, which was used by Andrew Selleck, Kathy Clark's student who we had to enroll to join forces. And now is working on producing a model that has everything in it, from X-rays to XUV, etc. So this will come out later on. The other thing that we did is we joined forces with the AIP in Berlin to look at the interactions between MHD winds and photooperative winds. So as I said, you know, those lines, it's very clear that everything is happening at the same time, but what is actually dominating the evolution? This is the main thing. You know, you can't always do a super complete model for everything, particularly if you're doing population synthesis. So it's important to know when things and what is dominating where. And so what you see here is again a disk, and you see the flow coming out of the disk and the magnetic field lines that basically thread the disk. And this was a student of Oliver Gressel in the AIP, Eleftheria Serafino, was now moving to London to continue this work at Queen Mary. And you see basically that what she found out, concentrate now only on this plot. This is basically the mass loss in the wind combined with MHD and photo operation. And this is a pure photo operation model. And what changes on the x-axis is the X-ray luminosity. So how much the X-ray is divide. And you see that actually the magnetic component, the difference between the MHD with photo operation and photo operation only becomes high when you have very low X-ray luminosity. Now, a typical X-ray luminosity for the solar time star is about here from the center of the but there is a 2 order of magnitude. So in theory, you could also have this type of situation. So, and this is important work because when you do your population, you have to draw the star according to the full population of possible X-ray luminosities. But you know, it's not doing too much wrong if you ignore the MHD with start with or your typical star. If you're only interested in the total mass, so how fast it is. Of course, structural doing changes completely if you have the MHD or not, which will also affect the estimate. The other thing that you see is that the big changes are also only seen, and you see this here, when you have the plasma parameter. This tells you how strong the magnetic field is in comparison with basically the pressure support, the thermal pressure support. And you see that the big differences are only really happening when you have a strongly magnetized. And so what I'm hoping is that it's going to happen in the next 5-10 years is that we really get observations of how magnetized these are to see in which regime we really are. It's clear that magnetic processes are happening, but it might be that they are not as prominent as we think, and they might be useful to drive accretion onto the star, but maybe together with also other processes. So this is something that jury is out. We need to wait for the really observations. It might be that by looking at emission lines, we might even check whether this really strongly magnetized disk wind exists. And with this, that's what I showed you, strongly magnetized. Yes, you get a really dense column of wind. If you see this, when you look at emission lines, the emission lines will then all be emitted from here, right? Because and so if you do that, for example, look at a typical diagnostic, which is 6301, this is the emission regions telling you where the line is coming from. And you see that basically if you have the MHD dominated, it shifts very close to the star and very high up with very high velocity compared to like a normal thermal wind. And so this is what it looks like in terms of the different profiles. So we might be able to really now check when the surveys become larger, what percentage of this are in agreement with this picture. So in some way you can use the line observations to tell you something about the magnetization of the disk. This is possible. Of course, it's a very indirect way. Measuring it in other ways might be easier, but it tells you how magnetized disks are where you care. In the planet formation region. Whereas the other observations might tell you what's happening at 100 AU, which is as relevant. Okay, so what we also did is forget about the planet formation model. We just put a planet in a disk and let it photo operate. And then what happens to the interaction of the planet? This is okay? Okay, good. Hello? It's better? Okay. So this is basically a simulation, a 3D simulation showing the work of Michael Weber, PhD student just finished, where he put basically a Jupiter in a disk and did a 3D simulation of a photo-operating disk with a forming Jupiter. And what you see, the green lines here are basically the flows that end up onto the planet. So the point of doing this was to understand how the presence of a planet influences the wind and the wind kinematic, and how the wind kinematics and the wind itself influences the formation of the atmosphere of this planet. So again, this interaction between the two phases. And what he came up, what Michael found out, he found lots of things out, summarized here, is that the wind diagnostics, so the wind kinematic is very much affected by the presence of the planet. So here basically, again, is the surface of the disk, and here's the wind, and you see basically the arrows tell you where the wind is going. And you even have wind coming back in, filling up the gap that you wouldn't have without the presence of the planet. And indeed, you do see this in the line profiles, but what you see the most is the variability of the line profiles due to the spirals that the planet produces inside the disk. And it looks like something like this. If you have 100,000 resolution, We compared with the available observations, and unfortunately, at the moment, we don't have observations at that type of resolution. We only have 45,000, and so we couldn't say yes or no. But of course, this situation might change in the very near future. And so this is why this kind of, I think this kind of avenue could be interesting in terms, again, of an indirect detection method for an embedded planet in a disk that's outflowing, and basically most disks are outflowing. What we also did is also try to see how the material is redistributed in the disk if you do allow for outflows. So in general, you think, you have a Jupiter here, and then you have very much a separation between the material from the inside to the outside. Now, what I'm about to show you is basically these are trace particles that were put into Pluto, and how this is the material that starts basically between 2 and 3 AU, and there are two simulations. The planet is here, and this is a simulation without photo operation, and this is a simulation with photo operation, and these are the two face-on images. So if I let this run, you see that the wind is basically messing everything up. So the material from the inner disk with the wind gets easily distributed in the entire disk. And if you have a simulation without photo operation, you have this segregation here. And so this is something that's interesting. Of course, you have to, you can't have your pebbles going outside through this process. The material has to be dynamically coupled with the gas. So small dust can do this, molecules, etc., etc. But so this is not a way to mix up the CAIs. So I'm looking at the case there. But you can have, obviously, processed material from the inner part of the disk reaching the outer disk in this way. So it may affect, for example, crystallinity of other measures. And we want to bring this forward in the next few years. And so this is basically summarizing all the things that he found out with this. And I'll just point you out the main things. Most of it I've already talked about. That what we also found that disks that have a planet in them live longer, because the planet doesn't allow all of the flow to leave the system, but basically recycles some of the material back. And so there are some disks that are seen to be very long-lived. And of course, it could be late in fall. Of course, mostly is probably that. But this process is also effective to increase the lifetime of this disk by at least a factor of 3. And we know the planets form. Now, of course, the caveat of all this is that this interaction is the strongest when the planet forms at the gravitational radius, so where the wind is strongest. Of course, if you form a planet 100 AU, it won't care about the wind, and the wind won't care about the planet. So it's only for those planets that are formed within 1 and 10 AU, which I guess these are most. So now for a change of topic, which is, however, completely related to what we're talking about, I'd like to tell you that we started also thinking about how to link some of what we have learned about this for planetary atmospheres. Why? Well, clearly there's a lot of new data that is coming over the next few years. And of course, this is Ariel, which is coming in 2930. And this will be the first spectrograph in space dedicated to the observation of the atmospheres. Of course, you can do it with JWST, but then you have to get time, and you have to, obviously this is a general purpose instrument. But I see this is a planetary atmosphere instrument, which will have a survey of exoplanets. However, it will not be the first. Before that, the little Twinkle is coming. So Twinkle is a smaller version of Ariel, has the same PI, Giovanna Tinetti at UCL, and it's basically really everything is small in Twinkle, but everything is cute. So you have a small mirror, but you have a very high sensitivity, and you're looking in a region which hasn't been looked at before, of course, by JWST, but for the very small number of observations that you could have. Whereas here you have basically a 3 to 5 year mission, also even 7 maybe, in which we will be able to survey and go back to the same planets over and over again. So this will be really something that will be nice to look for long time span observations of exoplanets. And we are founding members in this small mission. We're hoping that we'll fly in 26, 27. And we have lots of plans for it. So these are basically some of the science teams that we lead in Munich, looking at cases and pHs in the atmosphere of protoplanetary disks and exoplanets. Is something that we've already started working on. And so I'd like to say a few words about what we found out. First of all, pHs. Why? So most people find pHs either boring or annoying or just useless. So chemists find them useless. You know, they just stack on top of each other and do absolutely nothing. However, it turns out some people, including myself, find them really interesting. Reason for that is that they completely dominate the thermodynamics in atmospheric gas. If you are irradiating the gas with FUV, if you don't have pHs, you end up with cold gas. If you have pHs, you end up with warm gas. And this affects, of course, also photo operations in regions where the X-rays aren't as effective and FUV photons dominate. The same could be happening on exoplanet atmospheres. My colleagues in the biophysics department tell me that they don't find them that bad, because of course in their normal form, they also find them bad and boring. But if you manage to strip off one of the carbons and put a nitrogen in there, then suddenly they light up their eyes, because this is now asymmetric and everything can happen all the way to amino acids. So they say, I believe them. But anyway, I'm interested in this. And so we joined together forces in to try and understand how many pHs there are in this atmospheric gas, and what is the journey from the planet making gas to the planet itself. Now, of course, you know, people have looked at pHs forever, but pHs emit at long wavelengths like 6, 7 microns, 11 microns, famous bands. But those tend to be pHs that are mainly ionized. Neutral pHs have this very strong emission, 3.3 micron, and this is a wavelength region that is very difficult to observe from the Earth. And up to now, well, apart from JWST, which I ignore because they never give me time, it was only possible with ISO, you know, and ISO did not have very much sensitivity in this part. And so it could be that all the pHs that people try to observe in T-Tauri disks, so disks around solar type stars, and didn't find them, they only found them in 5 to 10% of the case, maybe they're there, they're just neutral. And we need to look at them at 3.3 microns. So this is what we want to do. And we want to look at them in planets. Is this a crazy idea? I asked a bunch of students because I had a paper, and obviously it was very simplistic, just plotted the opacity of the pHs and said, yeah, so you see, it's possible. Pathetic. Paper was even published. I don't know who the referee was. It's very clear that, of course, if you have other molecules and other stuff that are emitting in the same area, it might not be as easy to detect. So this is what my students then told me. But they tried. In fact, we first started to see whether we could make them in situ on planets with thermochemical equilibrium models. This was the Payan study. So looking at where we should look, what type of planets we should concentrate on. So this would be, for example, the effect of pHs in the transit spectrum of a planet. Then Fabian looked at available observations of exoplanets and found hints of it. But of course, the JWST data is missing, and we applied for it already 3 times, and they laughed. And so we still don't know if this planet has pHs or not. But if we had JWST data to cover the 3.3 micron range, you see this is where the models really change. And so this is the area which we need. So this is basically a calculated transit spectrum, and this is a retrieval that we make, which shows that we could actually detect them if they were there, even if they were there at only 1/100th of the abundance of the ISM. And so we hope that either they sometimes give us time, or that finally Twinkle flies and then we don't care anymore. Okay. And Rosa also has been working on this to try to see how the detectability changes with different parameters, particularly with the C/ρ ratio of the planet, which is something that links me back then to the disk atmosphere, but this is a different talk, a different talk, and so I can't go into the topic now. So now you are at the end of the talk, so I'll tell you something crazy because you probably now already fallen asleep. And so this is a project that we have had together with the biophysicists, so with Dieter Braun, in Munich, also thanks to the Origins cluster, but mainly in this molecular evolution in prebiotic environments, CRC. So I am the token astronomer in there. They're all biophysicists and chemists, so I understand absolutely nothing of what they're doing, but I try. And what basically they convinced me of is the importance of these wet-dry cycles on planets to basically let DNA strand evolve and become longer. Better if you have the right pHs, and not PAHs, but pH. So we had a few papers exploring where this could happen. Photochemistry was difficult, and so we decided to go to free-floating planets. Free-floating planets are planets that have been ejected from the solar system. They roam dark, so photochemistry free, and free in the galaxy. And there seems to be just as many free-floating planets as there are planets in planetary systems. So why not? And these guys can be ejected together with the moons. And so we looked at the possibility of having these wet-dry cycles on these moons orbiting free-floating planets. You might say, why are the moons warm? Well, they're warm because of the tidal interaction with the planets they have been ejected with. Through the ejection process, the eccentricity of the moon increases. And so this tidal heating is strong enough that you can have liquid water on the surface of this moon. So we published this paper, and then obviously something like this immediately has, you know, a lot of attention from the press internationally. So we had like an article in Le Monde on this, and came all the emails for people who really understood what they were doing from France, who told us this is absolute rubbish because your atmosphere will just simply collapse. CO will just condense and collapse, and so this is just impossible. And so we take criticism seriously, not too hard, because we have a life outside astronomy. And we decided to say, okay, you're right. You gave us the idea for the next paper. And so this is now what this PhD student is doing, David, again, in the CRC with Dieter, myself, and also with Tommaso Grassi and Karan Molavedicani, who know, I think, more about chemistry and atmospheres than I do. And what it's been doing is basically, it's been coupling the GG Chem, so a chemistry code, to Helios to develop now self-consistent atmospheric models for low temperature environment and really check whether these atmospheres are stable or not. And in fact, it finds that you can find stable atmospheres for certain atmospheric composition. And he finds also, together with Dieter Braun, that indeed this basically, there's certain types of chemistry in the atmospheres that could even stabilize more the high pH that they need for their wet-dry cycles of polymerization. And so this is really interesting stuff. These are the first steps, trying to basically join the community in Munich. And so we're looking forward to the next aggressive paper that we receive from somewhere else. But I think this is the way that you do things. You know, you try things and you put it out there. And, you know, of course, you can always do better. And this is what we're trying to do here in this paper. So summary, I summarize very quickly what I'm doing, just randomly a few things that I told you. PAHs aren't boring. They are important for disk evolution and planet formation, and they could maybe be detected even in planets. Don't forget that they've been detected on Titan, which is not hot. And so how did they get there? They probably got there still from the formation. So, and maybe we can detect them also in Titori disks with upcoming missions, and JWST if they give us time. So disk evolution and planet formations are very strongly intertwined. Of course, I'm not telling you anything new here. And something that might seem like just a surface process, like photo-operation, actually has a very important effect on the formation of the planets themselves. And you need to have it right in order to make simple population models of planets. MHD winds are important for sure. They are seen, but they might not contribute to the mass loss rates of disks that much unless you really have low X-ray luminosities or very strong magnetization. And finally, it would be very nice to continue this work on embedded giant planets with thermal winds. both because of their effect on the line diagnostics, so it could be a new way of finding embedded planets in this, just looking at the spectral lines, their effect on migration, effect on the lifetimes of the disks, which we have this so-called Peter Pan disks that we can explain why they live so long. Maybe this is helping. And also the effect on the atmospheric composition of the planet and the outer disks because of the inner gas redistribution. So I stop here. I have no idea. There's no clock here. So I hope that I didn't Thank you.
So, thank you very much. That was a great.
I hope that the people online didn't miss all of the talk.
No, I think it was fun. I think it was just a
Oh, okay.
questions, especially from students, postdocs.
Hi, Barbara. That was amazing. I have so many thoughts. But in particular, I really liked the in-prep work looking at the differences between MHD winds and photoevaporative winds and sort of making observational predictions. So one of the things we're finding with JWST is that we can spatially resolve extended disk winds in H2. And you talked a lot about the spectral differences in these wind signatures, but I'm wondering if this work could also make predictions for these spatial differences of these winds.
I already have a microphone. Sorry. I was now I want to use that one. You have to come down. No. Yeah, of course, we could in theory do this very easily. But at the moment, we are not calculating a chemical model of the wind set consistently. This was the first time that was done by Andrew Selleck. And so he now has plans of doing this with Prismo Pluto. With the models that I showed you, with Giovanni's models, which were done with Pluto using an XITE approximation, so a way to approximate the temperature based on photoionization models, we are actually limited to atomic or ionic species. And this is why we haven't looked at H2. The one paper where we looked at H2 was by post-processing our simulations with Prodimo. This was work by Christian Raab. But again, we didn't look at the spatial part because doing it that way with post-processing, you can allow for the fresh molecular material that is coming from the wind and from the disk interior that might come up into the wind. So what we do, obviously, if you do a chemical model of the wind, the H2 goes away much quicker and doesn't get replenished. And so we have plans to do this now with Andrew. So this would be really nice because indeed new observations also show this, but it's very large scales observations of H2 winds. This I can tell you already that we will not be able to match. Here, the something else going on there. There might be a wide scale magnetic process lifting this material also from large because photo operation doesn't come out to like 200 AU or something like this. So
More questions.
Yeah, Barbara, thanks. This was an interesting talk. So I had a question regarding the simulations you presented. You showed, I guess, some 3D rendering with some very large scale streamlines in the upper atmosphere, which I guess are the photoevaporative winds. How did you include those winds in your simulation?
You're talking about the 3D simulation?
Yes, the 3D.
Calculated actually set consistently. So what we do, we did it with Pluto in 3D, yes. And what we do, we update the temperature at every time step in Pluto using parameterization. So we calculate the ionization parameter at each point, which is only based on the column density and the X-ray luminosity and the density at one point. Which this was calculated using Mockity, so which is doing the whole radiative transfer process, and then we streamline to basically have this prediction, which means that we can update the temperature every time step of Pluto without any large overhead. And this is why we're able to do 3D simulation. And then the wind blows by itself, because if it's hot enough, then it gets unbound and the disk is spinning and the centrifugal force throws it out. And so this
Okay.
is why it looks like this.
Okay, that's super cool. Yeah, I mean, because yeah, I was wondering, was there, I don't know, maybe we can talk more about later, like how you can like, generalize this to include like, to work with like radiation hydro if someone wanted to include that. No, because that's super cool. I'm not so knowledgeable about photo evaporation, but
Neither am I.
come on,
I
don't
can
say it
say
like
it.
that.
Everyone has a level, right? There's always somebody more knowledgeable than you. So
More questions.
So is it the case that the cavities of the transition disks are all photoevaporated away? Or can you make the big cavities in the transition disks some other way?
oh, this the $1 million question. Actually, we don't believe that the big cavities are coming from photooperation. After so many years of transition of a research unit in which we try to make the big cavities with photooperation, we found only one way of making them, and this is in very low metallicity disks, which cannot be always the case. So actually, the problem with these very large cavities is that you always see, or very often also see, an accretion signature onto the star, high accretion, which basically tells you the cavity is not empty. You have a very high accretion, and you have a cavity very far out where photooperation is largely inactive. And so there, I think there must be other processes, and the obvious one would be an embedded planet, because this also allows you, as I said, a disk that is disconnected from the outside and the inside at some point loses the accretion signature because the inner disk drains from the star. If you have these long-lived inner disks that are clearly being replenished from the outer disk, and so this cannot be a completely empty cavity. Some of the cavities are also shown not to be completely empty. So I think that for the very large cavity with high accretion rates, planets are probably one of the possibilities, but there might be also other processes. This one that I showed right at the start, right? You talk. Yeah. So this I think that those cavities. So this one, you mean? No. Also the one on photooperation. Yeah. So this one. Yeah, I think that this is just to show how photooperation works, and I made the cavity here because I wanted it to be on the screen. But in general, the cavity from photooperation is made around the so-called gravitational radius. And so where the cavity is made, it depends from how heavy your star is and how strong your X-ray is. And the reason for that is that if you have a heavy star, then you have a deeper gravitational well. And so you basically need then a much higher temperature at the given, let's say if you make a cavity at a 1 AU in a 1 solar mass star, you only need maybe 1,000 Kelvin to go up the gravitational well. If suddenly you have a star that is 3-4 times heavier, then the gravity there, the flash is much higher, and so you need a much higher temperature. And the X-rays can't give you 50,000 Kelvin, they can only give you like a few thousand. And so then you have to move outside. So wait until the gravitational well goes up until photooperation can be active and make the cavity. In some stars that are really heavy, it might never work because you also have geometric dilution. So at some point you don't heat up the gas. And so it's only in those stars where the gravitational radius, which is basically where you can remove the material efficiently with the type of accretion that you have, that you can make this cavity. And so this is the problem when you have a cavity, observed cavity, let's say at 80 AU or 100 AU. The only way that you can make it by photooperation is if you make the cavity first at 10 AU or 5 AU, whatever, and then you eat up the disk from the inside out until you get to 80 AU, because then it's easier, right? Because then you have much more radiation, etc. And so in that way, you can make such a large cavity, but then you have an empty cavity, which is really large. And the accretion rate onto the star is very low because the inner disk is always dark. And so this is why I say that you can't make those large cavities, but you can make cavity between 1 AU and 10 AU, 15 AU. There's no problem. I used to have a plot of the transition with the demographics, but I will never find it now. It's much cheaper.
Well, thank you for this amazing talk. I learned a lot. It was a crash course for me. And I have a stupid question about, stupid curiosity about the free-floating planets. So I was really surprised to learn that they keep sometimes their moons, because I'd expect they are ejected by slingshot effect by few body interactions. So I would expect that most of them actually lose their moons when this happens. So how common are they, and
Depends very much on the type of encounter, let's say, that you have. So you basically you lose some of the moons. The idea is that you start with several moons around planets. So you see Jupiter, Saturn, they have several moons. And so we started off with having several moons around those planets and then let them eject. And some of them are lost. And some of them are, of course, disturbed by the ejection process. But that's a good thing, because it just basically means that they have like this very high eccentricity, and you have more time in which the tidal heating is strong before they circularize, which is, because once they circularize, then the tidal heating obviously is gone. And so, and this is why some of those moons may be only habitable for a very short time. But if you have a way of, like, you know, if you have several moons and, you know, maybe there's interaction with several moons, you can keep the electricity for longer. But this is all this is all stuff that has to be. So also we modeled that, as I say, with Ribbon, which is a very simple n-body code, and we found that most moons are retained. Also, like half of the moons are retained, half are lost, and the ones that are retained are very, very elliptical. But it depends also, you know, how close in the moons were to start with when the planet was ejected. And also it depends how many encounters the planet had before it was ejected that didn't result in an ejection, because this already kind of destabilizes the system. And then if the ejections come, then, and so, yeah. And the other thing to think about is that obviously not all moons are, you know, not just need moons, you need moons also that retain an atmosphere. And so the moons that we're talking about are almost the size of the Earth. So they're large moons around large planets. Yeah. So there's many things that you have to assume. The nice thing is they probably won't be observed, so we don't get some annoying observer to say, you know, like, oh, now we're more resolution, the spectral light thing. So this is why we decided to go for the most exotic thing. Next time.
These theorists. String theory. Yes. Yeah, so talking about this wet-dry cycle, so this must have happened on Earth as well, I guess, right? Because that's the whole theory of making these polymers or whatever. Okay. So you mean they always find an excuse that it works. Well, what I'm heading at is that if you say these wet-dry cycles, they work the best for these kind of exotic objects, then I was wondering, no, there's one place where we have evidence of life, which is here. Are you sure that these kind of wet-dry cycles then don't happen on more? Okay.
Have them on those, and because it's very difficult to model stuff with photochemistry for us at the moment, we wanted to start from a world where we can simplify things. And so, no, but certainly, you know, the wet-dry cycle. The thing with wet-dry cycle is that you need to have very small amounts of water to, you know, to have this wet-dry cycle. So this is also like the Earth is perfect. Yeah, the Earth is perfect for that. Yeah, no, of course, no, I didn't mean to say that the life is easier on moons around photo FFPs.
Another question.
Hi, yeah, thanks for the talk. I had a question about the PAHs on the atmospheres of planets, because I don't know much about them. But my understanding is that it is a bit not clear how these PAHs arrived in protoplanetary disks, if they were inherited or if they formed in the disk. Is this distinction a bit more clear in the atmospheres of exoplanets where you get higher?
The formation of when I took about pH with Tess some time ago, and when I took the chemistry, nobody wants to think about the formation of pHs. Actually, the formation of pHs, we did this thermochemical model, equilibrium model, very, very simple. I think it's very difficult to form them in situ on planets. At least this was Dorothean's answer was to that. They were very, and they depend very much. But you know, we didn't have photochemistry in there. It was very, very simple equilibrium models, and he found it very difficult. My thought that the way that they came into this is just simply from inheriting the gas from the ISM. So in the ISM there are pHs at the ISM level, and so unless they get destroyed, then I think that they will be inherited with the planetary gas. Then things can happen in the disk. So there were recent paper by Kevin Lange, who assumed that that they showed that one possibility for Titori disks being so devoid of pHs, or they not having been observed in many disks, 5 to 10%, is because what the chemists keep saying, they keep stacking together and they grow into larger clusters and then they sink and then you don't see them anymore. So it's possible. Why this doesn't happen in Herbig stars, I didn't quite understand from the paper, because Herbig stars, you see them actually 90% of Herbig stars. And so that's the big question. This is why we wanted to go in 3.3 micron to see whether it's just a matter of emission, that they're there and they're emitting differently in Titori stars. And in planets, it's the complete unknown territories. The only planet, well, on Earth, we make them in the barbecue very easily with the cars. But of course, so there could be a techno signature. But the only other place where we found them outside the Earth, or were found outside the Earth, is Titan. Not aware of barbecues on Titan. Who knows?
No, that we know of. Right. There's no more questions. Then there will be drinks with the speaker.
Yeah, so for the students, so PhD, master, bachelor students, there will be drinks right now, essentially after the talk. And sorry, yeah, right. And so this will be sponsored, so your drink will be free. No. No. And Jorge, he is the guy who will collect everybody here down. And then after that, we will have dinner. And dinner will be at the Marktplatz here of Neuenheim. So just here, just like 2 minutes walk from here. And if you are interested, please come down and let me know so that I can check if we need to reserve seats or not. Okay.
Okay. Thank you everyone for joining. Let's thank the speaker again.